Today we're going to be defining simple harmonic motion. So a simple harmonic motion is an oscillatory type of motion where the object moves back and forth about an equilibrium position. So the restoring force is always proportional to the displacement, and also the restoring force always points towards the equilibrium. So the condition for simple harmonic motion is that the force is equal to negative the constant k, the spring constant k, times the displacement x, and this is also known as Hooke's law. So the equilibrium position is where the net force is equal to 0. The displacement x is the distance from the equilibrium point, the amplitude a is the max displacement, and the period t is the time for one full cycle. The frequency f is the number of cycles per second, and that can be represented as f is equal to 1 over the t period. Now, if we want to find the formula for period, we multiply both sides by t, and then the t cancels out on the right, and then divide both sides by f, and then you have t is equal to 1 over f. Your period is equal to 1 over the frequency. So these are about the same. You just swap the f and the t. So for the acceleration, when you have simple harmonic motion, you also have to use Newton's second law, but you will just apply it to Hooke's law. So f is equal to ma, and then that will be negative k times x. So solving for a, then you will divide both sides by m. You have a is equal to negative k divided by m times x. So here we can see that the acceleration is proportional to the displacement. The acceleration is max at endpoints, and the acceleration is also 0 at equilibrium. And using angular, and also speaking on angular frequency, we have that omega is equal to the root of the spring constant k divided by m, and also that the period is... Continuing on with that, we can see that the F is the force that's like pushing it back against to where the natural position was, and X is the difference from the natural position. And also X doesn't matter because in the formula X is squared, so the distance is the same whether it's from the left or the right, since the square will always make it positive. Here we can also see some free body diagrams of what a spring looks like when it's compressed at different lengths. And here we can see that in a relaxed position, there's no force acting on the mass. But when the spring force pulls the mass to the left and the mass is displaced to the right of the relaxation, there's a force on the spring. And that is when you can see that on the bottom, it's pushed in, and then on the top, it's pushed out. And here, this is the system mass in the relaxed state. And then down here is the spring system mass for one cycle after the mass is pulled to the right, far position, and then released. So we can see that this can be modeled with a sinusoidal graph, which we'll see later at different points and stages of its cycle. Again, here we can see how the spring looks like when it's compressed, how it's here when it's 0 displacement, and here when it's varying at different levels. So this difference is negative x, and then this is positive x, and that's the equilibrium position, and then this is the stretch. 2 times the force and 2 times the displacement. So here again we can see the restoring force. Here there's 0 velocity, and the potential energy is at its max, and kinetic energy is at its max. The x displacement is at its max, and the force is at its max, and the acceleration is at its max for max compression, and there is a restoring force. At the equilibrium, or the natural state, there is no force acting on it. So the velocity will be the max in both directions, and your displacement is 0, because this is the equilibrium position that is measured relative from. The force is going to be 0, the acceleration is going to be 0, the potential energy is going to be 0, and the kinetic energy is going to be at its max. And then at the restoring force, we have that the velocity is 0, potential energy is at its max, the kinetic energy is at its max. Kinetic energy is 0, the x is at its max, the f is at its max, and the a is at its max. Now here we have some bar diagrams that really help to illustrate. So we can see at the equilibrium position, the kinetic energy is at its max. There is no potential energy, and we can also see the velocity will be plus or minus max. The displacement will be 0, the acceleration will be 0, and that's because the force is equal to 0, so that means negative k of x is equal to 0, so there's no acceleration. So we can see that down here it is at its equilibrium position. Now moving on to a stretched spring. At its max, the potential energy is it's all the energy will be converted into potential. So what we can see in all of these, what we will see is that mechanical energy is going to be conserved. We can see the velocity will be 0, the displacement will be positive A, which is the amplitude. The acceleration will be the maximum, and the force will be the maximum as well here. And then the same thing for when a spring is compressed, because x is squared, all that energy will 100% be here in the potential and here 100 in the kinetic. Again, these two are they're about the same. So we can see they are, only difference is that they are negative. And for halfway compressed, we can see about the same thing. They're both about the same, just negated. So we can see that it's just a mirror of each other. And this is why we get a sinusoidal wave at different stretches and compressions of the spring. Again, and to calculate the potential energy, you can use this formula. Potential energy is equal to x divided by a squared, and kinetic energy is 1 minus x divided by a squared. And that's because potential energy and kinetic energy, they have to sum to the mechanical energy. And so because it's conserved, you can just solve for one of them and then you can get the other one. So again, we see that potential energy is 1/2 of kx squared. Because the x is squared, the sign of x doesn't matter. So at equal distance from the equilibrium, the energy distribution will be the same. Also, your spring's constant will be k is equal to m times omega squared. And the total energy, again, is 1/2 k times the amplitude squared of the energy system. Here, let's focus on halfway compressed. The velocity is approximately 0.87 times v max. And the way we get that is we have velocity is equal to v max, the square root of 1 minus x divided by a squared. And then we know that x is equal to a over 2. So then plugging that in, we get v max divided by 1 minus 1 over 2 squared. And then v is equal to v max square root of 3 over 4, and square root of 3 over 4 is approximately 0.866. So that's where you get your velocity from. And it's the same thing for the halfway stretched as well, where we can see that yes, your velocity will be the same because of the square. The x is going to be negative a over 2 because it's going to be the opposite. Because when you have your wave, it's going to be the opposite, which we'll see soon. All of these can be their position time, their acceleration time, and their velocity time graphs. They can all be modeled using sinusoidal waves. And then you'll see that there'll be different cosine sine graphs just shifted and also inverted. So acceleration is going to be your max divided by 2. Your force is going to be the f max divided by 2. And then over here, your acceleration is going to be negative a max divided by 2. And then over here, your force is going to be negative f max divided by 2. So here we can see the displacement, velocity, and acceleration graphs for a spring being stretched and compressed. So we can see here that the displacement starts there's 0 displacement, then it increases, then it decreases, then it increases again, then it decreases, then it increases, then it decreases. Here we can see that the velocity, it starts out large, which makes sense. When you're at the equilibrium position, your velocity is at its max. Then it decreases to 0, then it goes negative, then it goes back to 0, then it goes positive, then it goes back to 0, then it goes negative. And then for acceleration, we can see that the acceleration starts at 0, then it goes to negative, then it goes to 0, then it goes to positive, then it goes back to 0, then it goes back to negative, then it goes back to 0. And what we can see is that we have the position time graph, which is just the sine graph. This is just the sine graph. And then the velocity time graph is just shifted by 90 degrees. So we can see that it's just shifted. This is the shift of 90 degrees. And then for the acceleration time graph, we can see that it's just inverted relative to the position time graph. So this is the same thing. It's just flipped. So you just have a negative sign out in front. You could imagine. And again, if you know Hooke's law, we know that Hooke's law has Hooke's law's region, the force starts off like this, but there's a limit of proportionality and the elastic limit. And then after this point, this is when the spring breaks and it can no longer take the force. So now let's do some practice problems that demonstrate these ideas. So, okay, we have identifying simple harmonic motion. A block is attached to a spring and oscillates horizontally on a frictionless surface. Explain why the motion qualifies as a simple harmonic motion. Well, we know that it qualifies as simple harmonic motion because it has to obey Hooke's law. And we know that Hooke's law is going to be F is equal to negative kx. And because of this, we know that force is proportional. Okay, force is proportional to displacement, F and x. So that means that the force points toward equilibrium. Therefore, we know that acceleration satisfies a is equal to negative k over m times x. So that means that the motion is simple harmonic motion. A mass system oscillates with a period t. The mass is quadrupled. Find the new period in terms of t. So what's the period formula? The period formula is t is equal to 2 pi root of m over k. Now we want to substitute the new mass, t2. So that's going to be 2 pi times 4m divided by k. Then you're going to have t2 is equal to 2 pi times root of 4 is 2 times m over k. That's just going to equal to 2t. So therefore, it's going to be 2t. A mass attached to a string oscillates with amplitude a. Find the acceleration of the mass. So we can use the acceleration equation, which is a is equal to negative k over m times x. And we know that the max acceleration occurs at the max displacement. So that means x is just equal to a. Now if we substitute that in, solving for a max, we have k times m times a. Now if we rewrite this using angular frequency, we have omega squared is equal to k over m. So overall, because we know that a is equal to x, then we substitute that in there. And then we know omega squared is equal to k over m from the formula of omega over here. So then we can get a max is equal to omega squared times a. So a particle moves along the x-axis under a force given by negative 3x squared plus 2x squared. Determine whether the motion is simple harmonic motion. Justify mathematically. So we know that first, the condition for simple harmonic motion is that the F net, the condition must satisfy F is equal to negative kx, where the force must be proportional to displacement and opposite the direction to displacement. And if we analyze the force that we're given, we see that it includes a linear component and also a cubic component. So because we have this, we know that because the force is not directly proportional to displacement over x, the restoring force is not linear. So this is not simple harmonic motion because the force is not proportional to displacement alone. A mass oscillates on a spring. When the mass is displaced 0.20 meters from the equilibrium, it experiences an acceleration of 4.0 meters per second squared towards the equilibrium. Find the spring constant. So we can use the simple harmonic acceleration equation, which is A is equal to negative k over m times x. And if we use the magnitudes, we take the magnitudes of these, we want to solve for k, right? So we have k over m is equal to a over x. And then that's just a over x. We know that acceleration was 4, and we know that the displacement was 0.20 meters. So we have that that's equal to 20. Therefore, we know that k is equal to 20 over m by multiplying both sides by m. And we have k, so that is our solution. That's our spring constant. And we know the spring, we had know that the spring constant k is proportional to the mass. A mass spring system oscillates with amplitude A and total mechanical energy E. Find the maximum acceleration of the mass in terms of E, M, and A. So we can write the total energy at maximum displacement, and that's going to be E is equal to 1/2 of k times A squared. Now we're going to solve for k. So k is going to equal to 2E over A squared. To backtrack there, we know that we had to multiply this by 2, and we had to divide by a squared. Multiply this by 2a squared. Then we have that cancels out. And then, yes, we have here, so that's k equals E. And now we can write the maximum acceleration. So A max is going to equal to k over m times A. Now we want to substitute for k. We have k, and that is right here. So instead of k, we can take m out as a reciprocal, so we can write it easier, better visualize it. So we have a max is equal to 1 over m, which we factored out, times 2e over a squared times a, right here. And if we simplify that down, a max is just equal to 2e over ma. So that is our solution. Now, comparing two simple harmonic motions. System A has mass m and spring constant k. System B has mass 4m and spring constant 2k. Find the ratio of their two periods, TB over TA. So, what we can do is we write the period formula. T is equal to 2 pi times the root of m over k. Now, writing each period, we have TB and TA. TA is just 2 pi m over k, and TB is just 2 pi 4m over 2k. And we want to find, so we can just like this. So now simplifying TB, we have this is equal to 2 pi over the root of 2k, because 4 divided by 2 is 2. And now we can take the ratio of this 2 pi mk. We see that everything cancels out except for the root 2. So the ratio is equal to root 2. A mass spring system has an angular velocity omega and amplitude a. Find the speed of the mass when it is at its displacement. X is equal to a over 2. So we can use energy conservation. And using energy conservation, we know that the total energy is going to be equal to 1/2 k times a squared. And we know that the energy at displacement x is going to be 1/2 mv squared plus 1/2 kx squared, because it has which is equal to this total, 1/2 KA squared. So we know that the total is going to be equal to the kinetic energy plus the spring energy. So we have, if we substitute in x is equal to a over 2, then we can rewrite everywhere you have an x. So that's going to be 1/2 mv squared plus 1/2 ka squared minus 1/2 k, that's equal to 1/2 mv squared. So we want to isolate, and we also want to subtract from the other side too. So we have 1/2 ka over 2 squared, and that's going to be, simplifying this again, we have 1/2 mv squared. We have 1/2 ka squared minus, okay, so 2 squared, that's going to equal to 4. 4 times 2, that's going to equal to 8. So you're going to have minus 1 over 8 ka squared. And then this is going to be equal to, okay, 1/2 is the same thing as 4 over 8. And then minus 1 over 8, that's going to be equal to 3 over 8. So then you have 3 over 8 ka squared, and then you have 1/2 mv squared. So then if you solve for v, then we have v squared is equal to 3 over 4 times k over m a squared. Because what we did was we multiplied both sides by 2, and we also divided both sides by m to cancel out the 2 and also to cancel out the m. So now over here, we just take the root of both sides again. Just take the root of both sides, and then we have root 3 over 2 times omega times a, because we can also substitute omega squared is equal to k over m. And when we did that right here, so we have omega squared k m. So that is your final answer, boxed. So a particle's position as a function of time is shown to be sinusoidal. Explain why this alone doesn't guarantee that the motion is simple harmonic motion. State the required condition. Well, we know that a sinusoidal position time graph doesn't ensure simple harmonic motion. And that's because for simple harmonic motion to occur, you have to have f is equal to negative kx, Hooke's law, or you have to have acceleration is equal to negative k over m times x, which is just Newton's second law plus Hooke's law. So either way, you need to have Hooke's law. So for a motion to be simple harmonic motion, again, the force or the acceleration must be proportional to displacement and directed toward equilibrium. So the defining condition is that for you to have simple harmonic motion is you need to have a linear restoring force. It's not a certain shape of a position time graph. So let's continue on. A particle moves along the x-axis. The net force on the particle as a function of a position is shown to be a straight line with a negative slope that passes through the origin. So does this motion qualify as simple harmonic motion? So we can recall again the definition for simple harmonic motion, which is f is equal to negative k of x. So if we analyze the force graph, we know that we have a linear relation between force and displacement. We also know that we have a negative slope. And so we can draw that here. Force, that's the displacement, F against X, and the force points toward equilibrium. And this matches Hooke's law exactly. So relating the slope to the spring constant, if the graph has the slope is equal to S, then we know that F is going to equal to negative S times X, so then K is equal to S. So then K is, again, the slope, and then this is simple harmonic motion, because we can write that in the form of Hooke's law. A mass undergoes simple harmonic motion with amplitude A. Find the ratio of the magnitudes of the acceleration at x is equal to a over 3 and x is equal to a. So using this simple harmonic motion acceleration equation, we have a is equal to negative k over m times x. So taking the magnitudes of these, we have a and x. So that's going to be a, we're going to have to find a, acceleration a over 3, and also acceleration a. So that's going to be k over m times a over 3 divided by k over m times a, and that's going to equal to 1 over 3. So that's going to be your ratio. A mass oscillates on a spring. When the mass is displaced 0.1 meters from equilibrium, it experiences an acceleration of 2.0 meters per second squared towards the equilibrium. Find the angular frequency omega. So we can use the simple harmonic motion acceleration equation, which is a is equal to negative omega squared times x. So substituting in our values, we have 2 for the acceleration, omega squared, times our displacement of 0.10. So we can rearrange this for omega squared is equal to 20, dividing both sides by 0.10. So we have omega is equal to the square root of 20. And that's going to be in radians per second, because omega is similar to velocity, and velocity is meters per second, so this would be radians per second. Now we can do our next problem. A mass spring system oscillates with the total mechanical energy of E. At what displacement x in terms of amplitude A is the kinetic energy added to potential energy? So we know that your total energy again is going to be 1/2 of k times the amplitude squared, and we know the energy at the displacement x is going to be k is equal to E minus 1/2 kx squared. That's going to be the kinetic, because your kinetic energy, your energy again is going to be kinetic energy plus the potential energy spring. So that's just rearranging for that negative 1/2 kx squared. So now we can set the kinetic and potential energy equal to each other. So kinetic energy, we can set the kinetic energy and the potential energies equal. So we have 1/2 kx squared is equal to E times E minus 1/2 kx squared. So we have kx squared is equal to E, and we know that E is equal to 1/2 k times a squared, right from up here. Right, so then you have x squared is equal to a squared over 2. Then you have x is equal to a over the root of 2. A mass oscillates in simple harmonic motion with the amplitude of a. The amplitude is doubled while the mass and the spring constant remain unchanged. Find the new period in terms of the original period t. So using the period formula, we have t times 2, t is equal to 2 pi times m over k. And the amplitude is independent of this formula. So therefore, then we conclude that when you calculate the new period, it would be the same because the only thing we changed was the amplitude, and that's not involved in the calculation. So a particle has acceleration given by a of x is equal to negative 5x. Does this describe simple harmonic motion? So simple harmonic motion, again, is going to be a is equal to negative omega squared times x. And yeah, and the angular, that is simple harmonic motion. And now we have to identify the angular frequency. So omega squared is equal to 5 root omega is just equal to the root of 5. And then omega is going to be in radians per second squared. A mass undergoes simple harmonic motion with amplitude a and an angular frequency omega. Find the ratio of the speeds at x is equal to a over 2 and x is equal to the root of 3 times a over 2. So now we can use the energy-based velocity equation. So using that, we have v squared is equal to omega squared times a squared minus x squared. So we can compute the speed at x is equal to a over 2, which just means substituting in here wherever you see x. So then you have v1 squared is equal to omega squared times a squared minus a squared over 4. And then that's going to be 3 over 4 omega squared times a squared. And then now we also want to compute the speed at x is equal to the root 3 over 2 also times a. So that's going to be v2 squared is equal to omega squared times a squared minus 3 times a squared divided by 4. That is going to give you, distributing that, you have 1 over 4 omega squared times a squared. And from here, we can take the ratio of v1 over v2, and that's going to be 3 over 4 over 3 over 1 over 4, because we can see that they both have those in common. And you have to take the root of both sides because you want to get rid of that squared. So then you have the ratio is going to be root of 3.